Work done by a variable force we are going to start in this class. So, from the definition, when I told you something, that work done is what, Risha?
FD cos theta.
FD cos theta. FD cos theta, then I can write F dot S or F dot D, whatever you want to take. Fine. So let me take F dot S in the vector form. It's a dot product actually, and the dot product gives a scalar quantity. Fine.
Yeah.
So, okay. I told you, the concept I told you is F is a constant force here.
Yeah.
F is a constant force, and okay. So work done is F dot S, where F is constant and S is the displacement for which this constant force is acting. It's not that we cannot take, if like the force is increasing. If the force is increasing, we cannot take the force, and then you do not know what force to take. So you have to take one element. Now this thing is going to come that if at a particular position there will be a particular value of force. For a very small displacement, we can assume this force to be constant. Like this, what is actually happening? If this O is there from the origin, and you are taking a body from O to like some position like air, and the force is increasing, and the force is continuously increasing, or it's like a variable force is there. So what we are going to do, for some duration, for some displacement, for some very small displacement like ds, we can assume this force F to be constant. We can assume this force F to be constant for some displacement at some displacement like at S displacement. After S displacement, the body goes ds, and during that ds, the force F was constant. So I can write dW, small work done during this ds displacement, equal to F dot ds. Got it? This is small displacement which we are talking. In this displacement, the F is constant, and because of that, we are getting this dW work done. So what I'm going to do now, this is dW, this work done is dW. Then another, I have to take some other distance like here again, and that's going to be like dW1, dW2, dW3, so on. So what I'm actually doing, I'm going to do integration. You're getting? I'm actually going to do, in order to calculate complete work done, what I'm going to do, I'm going to do summation of these small work done, dW. Okay, integration. That's going to be equal to integral F dot ds. Got it? This is how you do it when such thing happen, and then F must be given as some function of S, so you integrate it. This is generally you do. So for example, let me take one example here. The F force is varying with displacement as F equal to K upon X square, where X is the displacement from origin. Like from origin it is starting, and from here it goes, and this is the X displacement. A body moves from x naught to 3x naught. A body moves from x naught to 3x naught, and that force is given as a function of x. This is a force which is given as a function of x. Okay, so you have to tell me the work done in moving a body from x naught to 3x naught. Can you just tell me? now switch on your microphone for a while. How to do this type of question? From A to B, the body moves. Then what to do?
It's integral of f dot dx.
Exactly. So that what I'm going to do, like for at some displacement x from origin, I'm going to consider switch off your microphone. Switch off your microphone. At some displacement x from the origin, I'm going to consider a small element that's called dx. I'm going to consider a very small element dx. And for this small displacement, I can consider this force to be constant. You won't say, sir, at x it was f upon x square, and at x plus dx it's going to be x plus k upon x plus dx whole square. Yes, obviously that's going to be, but since dx is very small that I can even ignore it. I can neglect that value. So for this displacement dx, the force remains constant, which is k upon x square. So what I'm going to do in order to calculate complete work done, I'm going to do dw f dot dx, and actually it is going in the same direction. So theta is 0. So f dx cos 0. F dx cos 0 actually. So that's going to be f dx only. Okay. So what I'm going to do actually, I'm going to put value of f as k upon x square and dx, and integral from where to where? Integration. I'm going to do in the integration from x naught to 3x naught, x naught to 3x naught, and this is going to be complete work done. Got it, Risha? This is how you do it. So what you are going to get? 1 upon x square. The integral is k is constant, so I'm going to take k common. 1 upon x square, you are going to do is minus 1 upon x, minus 1 by x, integration from x naught to 3x naught, and that's going to be equal to k 1 upon x naught minus 1 upon 3x naught. Actually, what you do, you put the first limit for first the value here, but because of minus 1, it will become minus plus. You can think in that way, and finally you are going to get answer as 2k upon 3x naught. Got it? So this is the work done in moving a body from x naught to 3x naught by a variable force f upon x square. Got it? So this is how you proceed. You actually move. So this is a work done by a variable force. Now I tell you a bit about spring force. Bit about spring force is a question from by taking question only. We are going to do this one. Okay. See, this is, I'm going to take a spring force. Let me use some different color. That's going to be beautiful. Maybe this is a spring. You can see a spring of constant k. A spring of constant k. K is a spring constant. Okay. You are moving a body. It is at initially it is at its natural length. Natural length means it is not compressed. It is not expanded. It is in a very relaxed position. There is no expansion or compression in between. Now, what you do, you expand this spring by x naught. You pull this spring and expand it by x naught. Okay, you expand it by x naught. Fine. So what do we have to find out? We have to find out work done by force. Actually, obviously, you have to exert a force here, F. Work done by force in order to slowly. Now, see the significance, see the concept of each and every word which I am going to tell you now. It's work done by F. You are applying F force in this direction. Work done by F in order to slowly. This word is very important. In order to slowly elongate. In order to slowly elongate the spring. In order to slowly elongate the spring. By x naught. Got it? Now I tell you the concept of this word slowly. This is a very important word when you study dynamics. Slowly. What does slowly mean? Slowly means you are going to put this spring in such a way that it's always in equilibrium. Always. That means slowly means there is no acceleration. Always in equilibrium. There is no acceleration. It is always going to be with constant velocity. Always in equilibrium means no acceleration. Acceleration equal to 0. That means if at this point, if you are pulling a body from natural length, means relaxed length of spring to x, if it goes by x, so the force which spring will exert in opposite direction is going to be kx. Okay, Risha? It is going to be kx. Fine. And this force is varying as you are increasing x. This force will keep on increasing. Here it is f kx. If you increase by x1, then it's going to be kx1. If you increase more, then the x value will increase, and that's going to be kx2 and likewise. So it's a variable force actually. Variable force. So what I'm going to do at some x extension from the natural length, I'm going to consider a force kx. Obviously, the spring force. This is spring force. Spring will try to regain its shape, so it will pull the body, the external agent in opposite direction by a force kx. Okay, with kx force, it is pulling a body in back direction, right? So, and at x displacement, I'm going to take a dx element. For this dx element, I am going to consider this force F equal to kx to be constant, as we have done in the previous question. This is a dx. So exactly, this is a dx element I am going to take. So exactly equal amount of force if I apply in this direction, equal amount of force F I apply. F by me means F by external agent. I can write Fe. F by external agent, if that is equal to kx, exactly equal to what spring is applying. See, so at this point, in this direction, I am applying kx. Spring is applying kx. So total force is going to be kx minus kx. So that's going to be in equilibrium. When it's in equilibrium, so that means acceleration is 0. So with a very small velocity, with a very a very uniform velocity, it will with a actually at this point, it acceleration is 0. That means velocity can be 0, velocity cannot be 0. But since it is slowly, so with almost negligible velocity but uniform, the spring is going to be extended. So this is the concept. That's why you have to write slowly. Okay, this is the concept. So now I can write this work done is equal to integral f dot dx. What we have done here, can you see f dot dx and f dx cos 0, f dx cos 0. Obviously, I have to do f dx cos 0 from here, and the for dx, what was the value of f? I am going to put for dx. I am going to put the f. I am considering the f to be constant, which is kx. Kx dx. Okay. Integration from where to where? Integration. For example, I am taking from this position. I am taking extension 0 to x naught. So integration from 0 to x naught. This is the work done by external agent in pulling a body, in pulling a spring slowly. This is very important. So integrated kx dx, that's going to be kx square by 2. So answer is going to be 1 by 2 kx square. And that's how you know, that's how you actually know k half kx square, kx naught square. I was writing x naught. So that's how you get to know the work done by external agent. This same work done by external agent gets stored in the form of potential energy. That's why spring potential energy is same as half kx square, we write, when it is extended by or compressed by x. So this is potential energy stored in the spring also. Potential energy stored in the spring. Got it? Potential energy stored in the spring half kx naught square. This is how you do it. Hope everything is clear now. So in case I have to extend a spring from x naught to 3x naught, so if I have to extend from x naught to 3x naught, so only limits are going to be changed. Here you are going to put x naught, and here you are going to put 3x naught. Integrate it and get the value. Got it? So this is how you deal with variable forces. Quite easy and quite interesting it was. So here ends the concept of variable force. Let's move to a very important concept, which is power. We are going to deal with power. Power means power is rate of doing work. You know it very well. Rate of doing work. Everyone knows that. Or the rate at which the energy is dissipated or energy is getting stored. We can say rate of doing work. Okay. So this is a definition we always study. Rate of doing work. Okay. So I can write the power equals to P equal to dW over dt. Fine. dW over dt means dW is what? dW is a force, constant force, dot ds. dW is f dot ds. It is a force. It is a work done during ds displacement by constant force F, which we have just seen here. This one, dW is constant force F dot dx. That's why you are and the duration of time in which it is happening is dt. So it is dW by dt. You are going to take, and the units it is going to be joule per second. Okay. we also have one unit that's called watt. 1 joule per second is 1 watt. Okay, it is because of the scientist James Watt. Okay, Drishyam. Now directly go to the question how the questions can be asked in SAT. P is given as k t square. If the power is given is varying with time, power is a function of time. As you are increasing time in seconds, like if you have time equal to 1 second, at 0 the power was 1, t equal to 1 k, t equal to 2 4 k, t equal to 3 9k. Okay, so you have to tell me work done from t equal to 0 to t equal to 2t naught. Work done from t equals to 0 to t equal to 2t naught. Okay, dw is going to be equal to integral kt square. Okay, dw is going to be equal to p dt. Okay, dw from here I can write dw equal to p dt. dw equal to p dt. Okay, so that's what I'm going to write dw equal to p into dt, and integration from 0 to 2t naught. Isn't it easy? Quite easy. So that's going to be equal to k t cube by 3, k t cube by 3, k t cube by 3 from 0 to 2t naught. Okay, and that's going to be equal to what? 8 kt cube by 3. Okay, quite easy. This is how you actually move and do this. Okay, next one I am going to take. Power is equal to dw by dt. Power you have been given as dw by dt. Power equal to dw by dt. So I can write dw as f dot ds. F dot ds divided by dt. And what is this ds by dt? It's velocity in vector form. Actually, I should write when I'm putting in f dot ds upon dt. So ds by dt is velocity. So that's going to be f dot v. V is velocity at any instant. Got it? F dot v. Vector f dot vector v. So at the instant where you are going to put some value of f, and at that instant, what is going to be the velocity of what is the value of velocity you are going to put? So this in f vector dot v vector, it is true even if force is variable. It is true even if force is variable. Even if force is variable, you are going to this f dot v is applicable. So the value of v at that instant, what is the value of v at that instant? What is the value of v you are going to put and get the value of force? So that means even the force is going to be very near. If f is some function of v, so obviously it will keep on changing the velocity you have to put, and at each instant the power that being dissipated, it is going to be different. Fine. For example, there is this block, you are applying 50 Newton force. You are applying 50 Newton force, and at some instant, the velocity of this block is 10 meter per second. Okay. At some instant, the velocity is 10 meter per second. Obviously, you are applying 50 Newton, so the velocity will keep on increasing. Okay. So dw by dt, this value is going to be equal to power dissipated at this instant. Power at this instant is going to be equal to f dot v. And obviously, both are in same direction, so fv cos 0. So 50 into 10. That's going to be 500 joule per second or watt. Okay. This is how you do it. Okay, Risha? So this is quite easy and this is quite interesting. These are some easy questions and interesting questions which we actually do. And I think this much is enough for power. If you are given power as some function of t, then and you have to find out work done. How do? You integrate it as we have done. Okay, let's move. Let's move to another topic. I'm going to do one question. Okay. You need to tell me. This question is in horizontal plane. In horizontal plane, it is happening. Horizontal plane means this. In horizontal plane, what are you doing? You have tied a string at one end, and you are revolving this block. This block is tied to a string, and you are revolving this block like this. Got it? So I tell you. For example, that means you have tied it and you are in the horizontal plane, you are whirling it, you are revolving it, the block like this in the horizontal plane. Okay. Okay. So obviously, since it is going in circle, so there's going to be a centripetal force. Obviously, there's going to be a centripetal force, and you are moving it, you are revolving it with some constant velocity. Constant velocity is v. So constant velocity is v, and the length of this string is r, which is the radius I'm going to take from here to here. Okay. This is point A. This is point B. You have revolved it from here to here. Okay. And obviously, since you are revolving this block, so there's going to be a centripetal force, but someone has to provide that centripetal force. Who is going to provide? This is the tension. Tension is going to provide that centripetal force. Okay. So tension is going to be equal to mv square by r. Tension is going to be equal to mv square by r. So please tell me, what is the work done by tension in moving a body from A to B? Work done by tension in moving a body from A to B. Tell me this one. Yeah. Can you just tell me a bit? work done by body moving up. Do you think it is going to be work done by AB is going to be equal to T means mv square by R. Tension is mv square by R. We have just seen here. Into 2R. Because the displacement is from here to here. So answer is coming out to be what? 2mv square. Do you think it is correct? Switch on microphone. You can switch on microphone. I have done this mv square by R into 2R. Do you think it is correct?
Yeah.
Really? I cannot use this one. It is not correct. This is wrong. You know, the reason is what? Reason is the force direction is changing. The tension direction is changing. In this direction, at this point, the direction was this one. At this point, the direction was this one. At this point, the direction was this one. So the force direction is changing at each point. So force is variable because force is a vector quantity. It is not a scalar. Though it is mv square by r, magnitude is same, but direction is changing. So I cannot use this one. So what I'm going to do for like small displacement, this small displacement ds. For small displacement ds only, I'm going to consider this t to be constant. So Pw is going to be equal to what? F dot ds. Okay, because force is variable, and this F dot ds is what? Switch off your microphone. There's so much disturbance coming already. Switch off microphone. It's going to be T dot V. T dot V. Tension in this direction, velocity in this direction. Got it? I tell you. Sorry, the F dot ds. Okay, I just let me do this one. F means T in this direction. T in this direction towards radial. ds in this direction, tangential, and angle between them is what? 90. So the answer will come out to be 0. And if I say what is the power dissipated by tension, it is F dot V, tension dot V, velocity in this direction. This is also going to be 0 because cos 90 is 0. So work done by tension in moving a body from A to B or from A to anywhere, it is coming out to be 0. Got it, Drisha? This is the concept. Because F is variable, I cannot use this. Because F is variable. So I cannot use this one. No, I cannot. I'd have to go by integration. And actually no integration is required. Okay. This was a question of horizontal plane. Let me take another question of variable plane. Sorry, not variable, vertical plane. What I'm saying. Vertical plane. So it is like it is a vertical plane. So you are in vertical plane. You are whirling this now. You have tied with the string and you are whirling in vertical direction. So obviously it is going to be tension here. Tension has to act, and this is R is the length of string radius. Okay, you are whirling it with velocity v. Okay, from this point A to point B, you are whirling it. So tell me, work done by tension in moving a body from A to B. Work done by tension in moving a body from A to B. What? Work done by gravity. Work done by gravity in moving a body from A to B. What? Tell me. Yes, correct. Work done by tension is going to be zero, obviously, because every time the tension position and direction will change is going to be ds, and they are obviously going to make every time they are going to make 90 degree. Correct. This is correct. And this one, work done by gravity. At each point, the gravity direction will remain same. So work done by gravity is, we have seen earlier, F dot ds. Then you can see force into displacement in the direction of force. Displacement is from here to here in the direction of gravity is this only. So what you are going to have? It is of mass m. So force of gravity is, yeah, exactly, mg into 2r. Correct. mg into 2r. Correct. Force into displacement in the direction of force. Very good. Okay. So I think these concepts are clear. Now let's do one thing. What you have to do is energy concept. Let's do energy concept. We are done with these things. Let's do energy concept. Which color you like? Let me use green color. Energy concept. Okay. You must have studied energy in like 9th class or 10th class in your previous classes. And what is energy? Energy is the capacity of a body. Tell me.
Can we start next class? Because it's already 10.
Oh, okay, fine. Okay, so in the next class, we are going to study about energy. Yeah. Energy is going to be kinetic energy, potential energy, and work energy theorem we are going to study. In the next class, we are going to study kinetic energy, potential energy, work energy theorem. WET. Okay?